So I'll begin by recalling what we were doing last time. So what we were doing last time was this idea of sampling and repeated trials. The idea was to discuss sampling and repeated trials. And the first thing we discussed was this idea of Bernoulli trials. So and here the motivation was that you have an experiment where you're interested in a particular event in the experiment, and what you would like to do is if the event happens, you declare the experiment a success. If the event doesn't happen, you declare the experiment a failure. So what happens is that your sample space is reduced to just two possibilities: success and failure, and then the event space is just the power set of S, that is all possible thing. And the probability, the function from 0 to 1, is defined completely the moment you define the probability of success. And you define the probability is equal to P. P is the number between 0 and 1. If it's 0 means that there's no success, always a failure, and 1 means there's always success. And this is what we would call as a Bernoulli P distribution. So this is what we discussed last time, and then I said that if you repeat this thing again and again, you have independent Bernoulli trials. And I had done this example for you last time. I said that so I had done this example which I called as 2.1.1. Here we roll a die 2 times. And the question I asked you was that was a little different. I asked you what's the chance that the exactly 1, 6, and 2. Right? What are the chances that we have exactly 1, 6, and 2 rolls? And the way we did it was we had 2 methods. One was to outline all the 36 outcomes and then write down this event as our chosen event and description of it. And every outcome was equally likely, and then you divide by just the number of elements in this event, divide by total number of elements. That's one way of doing it. But the other way of doing it was that we said that the way to do it was you set up each roll as a Bernoulli 1/6 experiment, right? Because that's the success probability is 1/6. So the way you got this was you treated occurrence of 6 as a success, and then so that would imply that the probability of success is 1/6, probability of failure is 1/6, and the question you were interested in is that the probability of exactly 1/6 in 2 rolls, exactly 1/6 in 2 rolls. And this we wrote down as probability of success, failure, because you have only 1/6, and the other one was failure or failure success, or failure and success. This is what would happen in the 2 rolls. And then what would happen is that this is, since they're mutually exclusive, by the property of the probability, you could just write this as success. So it's success and failure plus the probability of failure and success, because they're mutually exclusive events, and by the axioms of the property of probability, you could show this. And this, now you use the fact they're independent, so you get probability of success times probability of failure, and plus here you get probability of failure times probability of success. And since now I'm in a Bernoulli 1/6 experiment, I know this is 1/6, this is 5/6, this is 5/6, and this is 1/6. And so I get 10 by 36. So just to sort of reiterate, what all we use? We use the fact here that we did two things. We modeled each role as a Bernoulli experiment, right? That's what we did to get this. And then at this step, we use the fact that they were modeled as Bernoulli 1/6 trials. So, and here we use the fact that of independence, right? So here, sorry, not independence, I'm sorry for that. Here we use the fact that they're mutually exclusive. So they're disjoint events, so you could add them up. And here we use the fact that they're independent, right? They're independent. And here I use the fact that they're Bernoulli, right? So in some sense, this is one way of understanding this this problem. So you could convert. So the way we did this was we said that we had an event of interest. The event of interest is exactly 1/6 in two roles. So we said that last time I said that I'm interested. Let's say A6 occurs in an experiment. So that is my success. And if 6 doesn't occur, that's my failure. So that's what each role is defined. Then I said that if I want to do two independent Bernoulli trials, because I'm throwing one role, another role, exactly 1/6 in two roles means that I have a success and a failure, or a failure and a success. That's the exact event that I'm interested in: success, failure, or failure, success in my two trials. And then I discuss independence and mutually exclusive to compute the problem. So your exact sample space for two roles would be the tuples: failure, success, success, failure, failure, and success, failure. And that would be your next sample space for your event of interest. But I did that calculation last time, and here I'm just computing this problem. Very nice. So now I will now try to generalize this. So now I'll try and say, now if I'm performing this role 10 times, let's say, I can't keep writing down my sample space and again and doing so as well. So now I would like to do something a little different. So I will just recall. So this probably you've seen in your 12th class substantially. Like, so if I have any two real numbers A and B in R, right, this is a fact, let's say, then for any integer n bigger than or equal to 1, then I know that A plus B to the power n is going to be equal to the sum from k equal to 0 to n choose k times A power k, B power n minus k, right? Where n choose k was just the number of ways of choosing k people from n people. That's just n factorial by k factorial and then n minus k. Very good. So now this is something that you should know how to prove. So I don't know if you have done this in analysis or writing of mathematics. So how does one prove a formula like this? So you should, if you haven't practiced it, just practice the proof by induction. So that's how you prove this. You prove this. So it's proof by induction. So this you must know that for n equal to 1, it's trivially true. N equal to 2, you assume till n equal to k, or n equal to m, let's say, and then n equal to plus 1, you try and show you. So this fact I'll assume that you know. So in probability, it's kind of very, in probability, it appears in a very natural way. This formula, which we will see in probability associated with Bernoulli P trials, with n Bernoulli P trials, let's say n independent of them, n independent trials. And here you sort of use the formula with A equal to P and B equal to 1 minus. See? So I'll need to use this formula. So in that case, I know that in that case I know 1 is equal to, if I add on this side, and on this side I'll have k equal to 0 to n choose k, p power k, and 1 minus p power n minus k. This is true for all n. So I'll use this factor. So I will require this factor. Okay, so now I will now do an example, and then by which I will illustrate this idea of n Bernoulli trials. In the example, this is the example 2.1.2. So here, what we'll do is we'll let n be equal to 1 be given. Okay, so some fixed number given to us. Then what I do is I perform n independent Bernoulli trials. So after performing an independent Bernoulli P trials, we are typically interested in the following questions. Like in the previous example, I performed it twice. I had interested in the following questions. So what are the questions we're interested in? So one question is, what is the probability of k successes? Let me mark the question in a different color. So the first question we're interested in, what is the probability of k successes? Mark it in red. So that's the first question I'm interested in. So I perform an experiment n times, n Bernoulli trials. Each outcome is success or failure. I'm interested in what's the probability of k successes. So this is called the Binomial Np Distribution. So I will this outcome space is called the Binomial Np Distribution on S. So I'll discuss what S is on S. So what is S? I'll discuss in a second. So what's happening now? Each trial, you're throwing out a probability. It's either a success or a failure. And success probability is P, and failure probability is 1 minus P. Right? So what you do is you let S to be the set of all tuples, that is omega 1, omega 2, up to omega n, such that each omega I is a success or a failure. This for 1 less than equal to I less than equal to n. So your experiment you perform n times. Each time you get a success or a failure. This is something that you keep in mind. Very good. So that's your set. And then again your event space is equal to the power set of S. That's also. So your probability is the function from f to 0, 1, and what's the probability going to be? Now your probability means it's a finite, S is finite, right? So notice that S is finite. So each place you have either only two outcomes, either a success or a failure. So there are two possibilities each position. So you can easily see that this space is finite. Now one needs to understand how to assign a probability. So now already I shown you before, if I know the probability of any single outcome, then I'm done, right? So now if I know the probability of any single outcome, right? A single outcome is what? Omega 1, omega 2, omega n, right? Then each omega n is either a success or a failure. How do I do this now? Now each trial is independent, right? So each trial is independent. Each trial is independent. Each trial is independent, right? Now, this is just going to be the product of each. It's going to be the product of I equal to 1 to n, the probability of each omega. Because all the trials are independent, so these events are independent. So therefore, the probability of A1 and A2 and AN is going to be probability of omega. So now this is also easy to see, right? So now we know that probability of success is P. Probability of a failure is 1 minus. Right? So immediately one can try and write this probability out. The probability of this product is just going to be P to the power the number of I such that omega I is equal to success, and 1 minus P to the power the number of I such that omega I is a failure. Okay, so let me just make this a little bit better. Move the cross. Sorry. Zero, 1, and then this is just this, and then here number of I is omega I is a failure. That's how you would assign the problem. See if it comes. It's coming. My internet is slow today. Very good. So now this is how you compute the probability of every event, every outcome. Right? So this exactly fine. Now this defines the probability on this case. There's nothing to be done. So what I'd like to do is I'd like to sort of now see what is the question of interest. Our question of interest is what is the probability of case successes. Right? So how do I do that? Let's see. So I have to have, let's say B. Let's say I denote B sub k. Let's say B sub k is the event that there are case successes in n trials. That is, there are case successes in n trials. In n trials. That's the event of interest. And I want to know, the question is asking B sub k is this, what is probability of B sub k? So here I've used independence, right? So independence. Very good. What probability B sub k? So here's the answer. That's the answer. So now you already know, because P is a probability, the probability of B sub k is the same as the sum from omega in B sub k, the probability of omega, right? Where omega is omega 1 up to omega. Now, you also know that probability of omega is just given by this formula, right? This formula here. So let me make this red perhaps. Red, red. Good. Move up a little bit. Small. So now I know the probability of any omega is just p times the sum number of i's omega I is success and number of I omega is failure. Now you note if omega is in bk, what do we know? There are k successes. That means we know two things. The number of I such that omega I is equal to success. Because omega is in bk has k successes, this has got to be equal to k. And the number of I such that omega I is a failure, that's going to be equal to n minus k. Because total number of people are n, so omega is equal to omega 1 up to omega n. So there are n people, and out of which k of them are success, and n minus k of them are failure. So therefore, from this, let's call this equation star. So from star, so therefore, omega is in bk. What's going on? Sorry about that. Omega is in bk will imply a probability of the single outcome omega is going to be equal to p to the power, the number of times is k, and 1 minus p to the power n minus k. What's happened to my pen now? Do one small jugglery and come back. So p power k and 1 minus p to the power n minus k. Because if you look at the above formula there, it's p times the number of I successes omega equal to success and number of I omega I equal to failure. So our success is k and failure is n minus k. Very good. So probably each outcome is p power k n minus k. It's the same for every omega in bk. So it's a constant. It's a constant. It doesn't depend on how the ordering is. It just depends on the total number of successes and total number of failures in the outcome. Therefore, now, probability of bk is going to be the sum over omega in bk. And for each probability omega, I have this formula. So it's p power k. So we have it down in green. So it's just p power k into 1 minus p to the power n minus k. So I'm adding the same thing again and again. So what will happen now? That's the same as saying this is going to be equal to the size of bk times this expression right here. This p power k. Sorry. P power k into 1 minus p to the power n minus k. So now I have reduced the problem of computing the probability to just understanding what the size of b power bk is. But size of bk, you all know, right? Size of bk means it's just you're performing n trials, out of which k is successes, and rest have to be failures. Right? So size of bk is just a counting problem. It's just the number of ways k successes can occur in n trials. But this is well known, right? This all you have to do is choose the spots for the k successes, and everybody else is a failure, right? So all you have to do is choose. So it's just the same thing as saying you choose k spots or k trials for success among n trials. But that you know is from 12th class or earlier, you know that is the same as n choose. Therefore, the probability of B sub k, which is your quantity of interest, is just going to be n choose k, p power k, and 1 minus p to the power n minus k. So that's your answer. That's your answer. And this is true for any k between 0 and n. Okay, let me recap a little bit. Where was I? Here. So what I do, I had n trials. I was interested in the probability of having k successes among n trials. And then the way I did was that I said let S equal to omega 1 to omega n be the outcomes in each trial. So each trial has outcomes success or a failure. And then I put this probability on it, which defined probability omega 1 to omega n. The trials are independent, so that means it's a product of the probabilities. I'm using independence here clearly. Right? So once I did that, I get a product of probabilities. But I know the probability of each omega I is given by either a p or a 1 minus p, depending on whether it's success or a failure. That means this expression right here is just p times the number of times you have successes and 1 minus p to the power number of times you have failure. Very good. So that's the expression for probability of every outcome. Now, since mod S is finite, we already seen before, if I know the probability of every outcome, that's enough to define the probability. Why is that? Because I look at the chance that I have k successes in n trials. I call it event as bk. But probability of bk is going to be just by the mutual exclusiveness property, summation of omega and bk, probability of omega. But omega is just a tuple omega 1 through omega. Now, omega and bk implies, omega and bk means what? That means bk is the event that there are k successes in n trials. That means you have omega 1 through omega n, k of them have to be success, and n minus k of them have to be failure. It doesn't matter which order they come, just want a total number. And that defines your B sub k. So that means omega in bk, probability of omega from this star is going to be p power k and 1 minus p power n minus k. So now you go back. Probability of bk is going to be sum over omega, p power k, 1 minus p to the power n minus k. And then that's going to be the same as size of bk, because every term is constant. So it comes out, it is size of bk times p power k, 1 minus p to the power n minus k. So mod of bk is just the number of ways of k successes can occur in n trials. That's just choosing k spots among n trials, and then just choosing it, and that's n choose k. So probability of bk is n choose k, p power k, 1 minus p to the power n minus k. Very nice. So I made one small error, so I don't want to call this the binomial. Though this is literally the binomial, I just want to bring this back here. Let me erase it and bring it back here. Okay. So now let me discuss what a binomial is in a second. So now let me go back to the original screen and close this class with that. So this calculation showed you how to compute the chance of k successes in n trials. Now what I do is, suppose I'm only interested in the number of successes, not anything else in the experiment. So what I'll do is, as in question. So we have n trials, and our only interest is in the number of successes. We don't know. We don't care about how they occur, what's happening. Otherwise, we are only interested in number of successes. So then, the way you do it is you redefine the sample space in the following way. Then, you could think of sample space as T. Let's say T as 0, 1, 2 up to k up to n. You let f be the power set of T. That is all possible. And then you let the probability of T to 0, 1 given by the probability of an outcome k is going to be just like here. So it's going to be k going to number successes. This is going to be n choose k p power k 1 minus p to the power n minus k for k in 0. And now I know it's a legitimate probability because if you have a finite set sample space, you know that you have a legitimate probability if the sum of the probabilities over all outcomes become 1. But that's easy to see. We know that the summation over k, probability of p sub k, that is p of s, p of t in this case, is going to be equal to this, is from 0 to n. So now here, t is equal to 0 to n. And this n choose k, p power k, 1 minus p power n minus k. And by our earlier expression of binomial expansion, this is just p plus 1 minus p to the power n, and that's just 1. So this is a legitimate probability. And this is called the binomial NP distribution. So this is called the binomial. This is called the binomial NP distribution. So when I say binomial NP, that means my sample space S is just 0, 1, 2 up to n, and the probability of every outcome k is going to be equal to, so we can call this as T, it's for the notation, and it's just n choose k, p power k, 1 minus p to the power n. So the binomial NP distribution models understanding the number of successes in n trials, where the probability of each success in each trial is given by p. So p is within 0. So this is the second distribution we have learned now, or third distribution. First was uniform, then was Bernoulli P, now binomial NP.